Welcome back, everybody. In this video tutorial, I'm going to talk about graphs of inverse functions. Now, in the last couple of videos, I just discussed what an inverse function is and how it is related to its original function. But in this video, we're going to discuss how we can compare the original function to its inverse. And you will start to notice a relationship between the coordinate points of both functions. Now, the graph of a basic function and its inverse are related, as I said. If there's a point AB that lies on the original function f of x, then there exists another point BA on the graph of its inverse. The graph of the inverse function is kind of a reflection or a mirror of the original function f of x in the line y equals x, as you can see in front of you. Now, I just went ahead and graphed some function. We have f of x, and then I went ahead and graphed its inverse, f inverse of x, across the line y equals x. So what this is saying, basically, is this is a reflection. Like if you just mirror this across y equals x and vice versa, they're just reflections of each other. The x values of f of x would become the y values of f inverse of x, and then the y values of f of x would become the x values of f inverse of x. Now let's go ahead and look at our example here. We have find the inverse of f of x equals 2x minus 3, and sketch both graphs showing their reflections in the line y equals x. Now I'm gonna leave this here just for reference, but we might have to move it because we're gonna need some space. So let's go ahead and find the inverse of the function. We have f of x is equal to 2x minus 3. And then following the guidelines I set in the previous videos, we're supposed to replace y with f of x just to make things a little simpler. And then with every y and x, just switch y for x and then x for y. And since we only have one y and one x, we're just kind of like swapping them. So x is equal to 2y minus 3. And then if you add 3 on both sides, you're going to end up with x plus 3 is equal to 2y. And then if you divide by 2 in each term, eventually you're going to get half x plus 3 over 2 is equal to y. And then, of course, don't forget to replace y with the f inverse notation. I'm going to go ahead and write this here, because I'm going to go ahead and erase this. We have f inverse of x is equal to half x plus 3 over 2. So we're going to go ahead and verify just to see that we got the right inverse function. So the way to do this is to take the inverse and then replace it for each x in the original function, which is 2x minus 3. So we're going to go ahead and do that. All right, verify here. So 2 times half x plus 3 over 2 minus 3. 2 times half x, that's just going to give us 1x, which is just x, plus 2 times 3 over 2, which is 6 over 2. That's just going to give us 3. Then we have negative 3 left hanging there. So x plus 3 minus 3, the 3's are going to go away, and then we're going to end up with x. And we can say that we have verified our inverse function. And we can go ahead and graph, or actually plot points, construct a table of values, then eventually plot our points. So we have x, and and f of x. Now I'm going to choose small points here. Let's say -1, 0, 1. And I'm going to go ahead and add a few more points just to get some accuracy. And then taking each x, plugging it in for the x in f of x, we're going to get 2 times -1 minus 3. 2 times -1 is -2. And then -2 minus 3 is just going to give us -5. For 0, we're going to get 2 times 0 minus 3. That's just going to give us 0 minus 3, which is just -3. We have 1. 2 times 1 minus 3. 2 times 1 is 2 minus 3. That's going to give us a -1. And then plugging in 2, we have 2 times 2 minus 3. That's 4 minus 3, which is 1. And finally, we have 3. 2 times 3 is 6. 6 minus 3 is going to give us 3. Now we're going to construct a table of values for the inverse function. And if you recall what I said before regarding the coordinate points, so the x values of this function, the original function, would be the y values of the original function. And then the y values of the original function would become the x values of the original function. So what we can do here, we don't have to do some math. We can just take all those y points, all those y values, and put them here. And then take all those x values and just put them here. That's going to give us -5. So at -5, we have -1. At -3, we have 0. At -1, we have 1. At 1, we have 2. I hope you can see this. I'm already running out of space. I'm gonna try to squeeze it in. And we have 3 and 3. So 3 and 3. Hope you can see this. I can just tilt the camera. Now we can finally go ahead and plot both functions on the graph. I'm gonna color code it. I'm gonna use green for the original function. So at -1, we have -5. At -1, we have -5. Well, the graph only ends at 4.5, but we can use the edge of the arrow as -5. So -1 all the way down here at -5. Then we have 0 and -3, which is here on the y-axis. We have 1 and -1, so 1 and -1. So somewhere here, oh, that's a little bit off. Right here. And we have 2 and 1, so 2 and 1, somewhere here. And finally, we have 3 and 3. So 3 and all the way to the top, 3. Somewhere here. And then this graph is going to go on forever, but let's go ahead and plot all, connect those dots. Excuse my sloppiness here. Notice this is just a straight line, basically. And of course, this is going to go on forever. Now we can go ahead and plot the inverse. And you're going to see something interesting here. So at -5, we have -1. So -5. Again, we can use the edge of the arrow here as our -5. and then at -1, so somewhere here. I'm gonna move this just a little bit lower. There we go. And then at -3 we have 0, so at -3 we have 0. So right there on the x-axis, we have -1 and 1. So right there. We have 1 and 2, so 1 and 2, somewhere here. And then we have 3 and 3. 3 and 3. So right on this line. And of course this is gonna go on forever, just like the first function. If we go ahead and connect those dots, roughly the sketch is gonna look something like this. Something like this. Now, y equals x is kind of off a little bit, I would say. Again, excuse my sloppiness, but you can see what's going on here. There's a reflection on y equals x, and at point 3, 3 in both functions, that's when you start to see the two graphs intersecting. So recall what I said before regarding how the coordinate points are switched. This is kind of interesting actually, because this is a perfect example of reflection, and to show you the relationship between the regular function and its inverse. And we're also going to reintroduce this concept when we cover one-to-one functions. And then you can also plot whatever points you want, of course, because mainly this is just sketching. But eventually, if you have a function and its inverse, and you have verified that the inverse function is actually the inverse of the original function, then this concept of y equals x will apply for any type of problem. I'm gonna try right now to think of more examples, and I'm gonna post a couple of more videos as well. Please don't forget to hit that subscribe button, and please go ahead and like this video. This is going to help grow the channel more. If you have any questions or concerns, don't hesitate to leave a comment in the comment section below, and we'll see you in the next video.